When we studied translational equilibrium, we focused on masses that we could consider to be pinpoints, meaning that we can imagine that all the mass is concentrated right at the center of the object. But what happens if the object is suddenly a long shape, like a board or a plank? Suddenly, the arrangement of the forces matters. Not just how they act on the object, but where they act on the object is also important. To initiate our study of this, we're going to look at a seesaw. Everybody's experienced a seesaw before. If I take a small boy, 20 kilograms, and place him at one end of the seesaw, and use the same boy, imagine they're twins, at the other end of the seesaw, same distance away, 20 times 9.8 gives us a force of gravity that's straight down of 196 newtons. And if I click on the force button on the upper right, I see my two white arrows are equal forces acting on opposite sides of the teeter-totter. Now if I remove the supports, I think we can all predict what will happen. Nothing. They'll stay perfectly imbalanced on the actual seesaw. Now if we continued our free body diagram, I've got my two forces of each child on either side, 196 newtons down on this side, 196 newtons down on this side. The only force that's holding the beam up, and that's what we're focused on, is the forces acting on the beam or the seesaw itself. The only force that's holding it up acts right at the pivot of the seesaw, right in the middle, and it would be straight up with a value of 2 times 196 newtons. So in other words, translational equilibrium is still true here because this system is not accelerating. So forces down have to equal forces up and everything remains stationary. So we would have a force directed upwards of 2 times 196 newtons. Now what happens if we shift the position of one of our kids? Let's put the supports back and move one of them in. So he's sitting closer to the pivot point. Still 196 newtons down, still 196 newtons down on the left, but we know now from experience when I remove the supports, the beam is going to rotate. And we can see that the left-hand side wins. So clearly the location of that force in relation to the pivot actually makes a difference. And we call that a torque. The further away from the pivot point I am, the greater the torque that this child is exerting on the pivot. And it causes the beam to actually rotate. We say that torques are a vector, but instead of saying left, right, up, down, north, south, we say it rotates counterclockwise or clockwise. So the child on the left will exert a counterclockwise torque, and the child on the right is exerting a clockwise torque. The arrangement of the forces is now important, where they are in relation to the pivot point. Let's examine this relationship between the force exerted and the distance from the pivot point a little more thoroughly. So I'm just going to reset everything, and we're going to use bricks this time because they're easier to manipulate on the beam itself. We're going to add a ruler, and the ruler is giving us distances from the pivot point. It turns out with torques you always want to measure distances from whatever it's rotating about. So if I put a 10 kilogram mass at the 1 meter mark, eventually I'm going to remove the supports. I want to know where I'd have to place this 5 kilogram mass to balance it. Now, it doesn't take much to realize that if I put it at 1 meter, so that they're the same distance apart, so here on the left I've got a large mass of 10 kilograms, on the right I've got a smaller mass of 5 kilograms, both 1 meter from the pivot. If I remove the supports, obviously the 10 is going to win. Now, if I go back and take my 5 kilogram mass, I think most of us with our experience with seesaws before would understand that we'd have to move it to the right. We've got to get further out. The lighter kid always has to slide his butt towards the end of the seesaw. When I remove the supports here, the 10 kilograms still wins, but maybe not as vigorously. Let's put him back. Slide it out a little further. Almost. And here we see we're in balance. I can even remove the ruler and see what it looks like. So we have double the force on this side and half the distance. Here we've got half the force and double the distance. So if we just simply multiply force times distance and get that value to balance, then we say we're in rotational equilibrium. And we call that product of force times distance a torque.